What's poppin', YouTube? Code Adventurers, welcome back to the Advent of Code 2023. Chris here, and last night we traded the cosmic wonders for the soothing heat of the hot springs, unraveling the mystery behind the lava's shortage. We dove deep into the arrangements, unfolded them, and with the power of recursion and pattern caching, cracked the code in record time. If you missed the thermal coding action, catch up, because tonight we're setting sail to Lava Island for day 13. And I've got my coding sunscreen ready for another adventure. I hope your coding shades are on and you're packed some coding sunscreen because things are about to heat up. If you haven't joined the Code Adventurer crew yet, hit that subscribe button, give a like, and if you're ready to explore the lava-soaked challenges of day 13, ring that bell to stay in the loop with all things Advent of Code. After soaking in the hot springs and successfully managing the lava arrangements, I'm stoked to see what Volcanic Challenge Day 13 has in store for us. So grab your sunscreen, clear your coding beach, and let's code our way through the molten landscape for Day 13 of Advent of Code 2023. Code Adventurers, are you ready to brave the lava and conquer another coding challenge? Let's erupt into another coding victory. Day 13, Point of Incident. With your help, the hot spring team locates an appropriate spring which launches you neatly and precisely up to the edge of Lava Island. There's just one problem. You don't see any lava. You do see a lot of ash and ingenious rock. There are even what it looks like gray mountains scattered around. After a while, you make your way to a nearby cluster of mountains only to discover that the valley between them is completely full of large mirrors. Most of the mirrors seem to be aligned in a consistent way. Perhaps you should head in that direction. As you move through the valley of mirrors, you find that several of them have fallen from the large metal frames, keeping them in place. The mirrors are extremely flat and shiny, and many of the fallen mirrors have lodged into the ash at strange angles. Because the terrain is all one color, it's hard to tell whether it's safe to walk or whether you're about to run into a mirror. You note down the pattern of ash and rock that you see as you walk, your puzzle input. Perhaps by carefully analyzing these patterns, you can figure out where the mirrors are. To find the reflection in each pattern, you need to find a perfect reflection across either a horizontal line between two rows or across a vertical line between two columns. In the first pattern, the reflection is across a vertical line between two columns. Arrows on each of the two columns point at the line between the columns. In this pattern, the line of reflection is the vertical line between column 5 and 6. So we've got basically an above and a below. Because the vertical line is not perfectly in the middle of the pattern, part of the pattern column 1 has nowhere to reflect onto and can be ignored. Every other column has a reflect column within the pattern and must match exactly. Column 2 matches column 9, so on and so forth. The second pattern reflects across a horizontal line instead. This pattern reflects across the horizontal line between row 4 and 5. Row 1 would reflect with a hypothetical row 8, but since that's not in the pattern, row 1 doesn't need to match anything. The remaining rows match. Row 2 matches row 7, row 3 matches row 6, and row 4 matches row 5. To summarize your pattern notes, add up the number of columns to the left of each vertical line of reflection. To that, also add 100, multiply the number of rows above each horizontal line of reflection. In the above example, the first pattern's vertical line has 5 columns to its left, and the second pattern horizontal has 4 rows above it, a total of 405. So just 5 straight count from the columns and 400 from that. Find the line of reflection in each of your pattern. It's in your notes. What number do you get after summarizing all of your notes? Okay, let's go and sketch up the problem. Let's take a look and see how we're going to solve this. So I already put this together briefly. Haven't done anything other than put this together. Let me move that. Okay. So the idea is that we're going to start, we can look at this first by scanning all of the columns, and then we can look at it scanning all the rows, but really it's just the same. You just can invert the matrix or you can change the way you approach it. But we're going to start with index I on the first column and index J on the second column, and we're going to compare we can use an arrow because we have arrows. We're going to compare the first bit here, the first two, and we're going to see that they don't match. So we're going to move our indexes forward. And we're going to compare, and we're going to see that they don't match on the first one. So we're going to move forward, and we're going to move forward. Same thing, these do match. So we're going to come down to the next one, and we're going to compare these, and we'll see that they don't match. So we're going to keep moving forward. And then in this one, this example I have here, the reflection point is actually here. And the way we know that is because if we go down each index here, 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 and here, they match. So now we found the midpoint of a reflection. And if we go back to this pattern, the line reflection is the vertical line. What I'm trying to figure out is, in the first example, the first pattern's vertical line has 5 columns to its left. So 1, 2, 3, 4, 5. Now, here's the interesting thing, is that we don't actually care whether or not it matches. So we're really just looking for, we don't really care about the full reflection in this particular task. We just care where the line of reflection is. And so the line of reflection, I think, can just be found by this process right here. So we found our line of reflection. So everything to the left of it, 1, 2, 3, 4, 5 is our answer. That should be it. I can invert this, but I won't take the time. But you would do the same thing for each row, where you would start at the top and you would compare the first two, and you would go 2 by 2 until you end up with something that matches. Now, this may expand to figure out just considering the reflection, which I think would have been a harder problem and probably more appropriate, where we would have to scan left and right to get the number of columns in the reflection, but it doesn't say that. In fact, this example proves it. We have this extra column off to the left that we are still counting in our total. So I don't really care about that. I just need to know where the reflection point is. Now, there might be some edge case where you may end up with, like, let's say all hashes and all dots, and then I actually have to consider more than just these 2 columns. But yeah, so it's just between 2 rows or 2 columns. So I mean, that it doesn't say to consider anything more, so we're not going to expand the problem beyond what it has to be. We'll go with the clues that we have, and so we're really only going to compare that. So we've talked about how we're going to accomplish that visually. So let's talk about programmatically. So I'm going to change this terminology to as string grid. And actually, I'm just going to call it as grid, and we're just going to assume that any grid is string, and then just to make things a little bit straightforward. But we can't just parse it. We actually, if you look at the input, so let's grab our test input. Our test input should be here. And if we pull that in here, notice that there's this double hard return here that separates the different blocks. So what we're going to do in our code is we're going to actually split on /n/n, and then mirrors is just a slice of string, because we're getting back a grid here. So this moves down here, and so that's going to be our individual mirrors. We'll print that, and So let's run a test, and we'll get our output here, undefined G. Yeah, we don't care about that. 1 mirrors instead. All right, so this is our slice of mirror. So now that we have our mirrors defined, we can define our function. And let's take in, which will be our mirror. And we're going to return above and below. So let's then loop through. So for, we'll say I, row in range of mirror, all right, so what we're going to do is we're actually going to, I is the row that we're on for each row. So we're going to walk through each row, and then we want to walk through if let's see here. So we could do a couple different things. Let me do this. I could do 2 different things. I could just create a Boolean operator, and then if they don't match, match equals false. I'm sorry, match equals false. And then finally, if we get here, if match equals true, return, really it's J and then J plus 1. Or I'm sorry, I and then I plus 1. We really don't need these. I don't think. And then for I, really we want for I is assigned 0. I is less than length of mirror minus 1. So the reason is we want I to not be, if we've got a slice of 10, which is 9 for the length, don't want it to go past 8 because we don't want to go out of bounds on that I plus 1 that we have. So we're going to do this instead, and then this will just be mirror sub I. Yeah, we don't need that. So if we've got a match, then we're going to return it. But that only takes care of the rows. If we don't exit here, then we've kind of got 2 options. We can just use the same method and kind of invert or rotate the grid, or we could just calculate it here and go column by row, which is what I'm going to do. So length of mirror sub 0, and then for J, range of, what we'll do is we'll switch these. And so anytime we don't have a match, we could just go ahead and break. And similarly, if we go through all of our eyes and we have a match, then we'll return J plus 1. Otherwise, we'll return -1, -1. So the only other thing here is considering if the type. So there's no real way to know if we're a column or row. So I'm just going to have a string that gets returned, and we're going to say row, and we're going to say call. And none. Or empty. And that'll allow us to do our math on it later. So I like to segment, let's see where we're at. So we got our mirrors, and then for mirror in range of mirrors, we're going to do type above, below, find reflection in our mirror. Oops. That's what I get for refactoring some stuff. Oh, definitely not that. All right, so what's the issue? Got it. So switch on T, case, we'll use a case statement here. Call, case, row, and then default is nothing. So if, let's look at our definition here. So if it's a column, we just got to count the ones to the left. So it'll just be a straight add. So score plus equal, and it's to the left. So above, should be a plus 1. And if it's a row, so 4, total of times 100. So I think that's our 4 or 5. And we'll just throw an error there. And then below we don't really need right now. So we'll go with that. Okay. No reflection found. All right. So if we run our test should be based on our, let me close others. Our test result should be 405. So let's go and run this. Interesting. 700. Okay, we've got 2 mirrors. Row 2. Row 3. Okay. So let's look at that. So 0, 1, 2. Definitely not right. All right, let's take a look here. We've got our first mirror, and we're at I, J, and 1J. So that is comparing. Okay, so let's look here. This first one, example, the first pattern's vertical line has 5 columns to its left. So this one has both. Every other column has a reflected column within the pattern and must match exactly. Okay, so I missed that, which is fine. So now we do have to, if we go back to our item here, if we find a potential reflection point, we have to then grow until we get to a boundary, which is here. And so we can see, because we're at a boundary, we don't have to go any further on this side. But it is a reflection because the furthest we can go on the right, we went on the left, and we have a reflection. So if we look at the other example where we didn't work, or what is our false positive, we're going this direction, and these two don't match. These two don't match. But these two do. And that's why we're saying we're okay. But if you expand up here and you expand down here 1, okay, those match. But then if you go down one more to here and to here, they don't, because the last columns here are mismatched. So here and here. So what we found here, I think is part of our answer, which is we have a reflection point, but we don't know that this is actually a valid reflection. So we've got the midpoint. So let's create a valid reflection. Func valid reflection. And we'll just take in the mirror. I think it makes sense to break this up. We'll take in the above and below of the end. And then we're going to think about this in the row context. Again, I could probably just shift the grid 90 degrees. But, and then we'd have less code, and maybe we'll do that later. But valid row reflection. So we need to check how many indexes we need. I think the way we do this is we need to determine not which one is min, but if we take the above, that's as far from the left as we're going to be, and then we take the below minus the length of mirror. So that way, this might be a 10. Actually, we got to invert this. If our total array size is 10 and we're currently at position 8, we know we only have to move 2 out. So whichever one is true. And so we'll just do for I 0, I is less than or equal to checks. Then we'll do I plus plus. Perfect. So now what we want to do is we need to check every, so this is going to be above minus I and below plus I. And so what that's going to do is we'll start at above and below. We're going to recheck, and then we're going to expand out, and we're going to return a bool. So this is just simply going to return false. And then this goes away. So now we can check to see and valid row reflection mirror I, J. Whoops. Not ready for that yet. This one is what I'm looking for. Okay, so this is I and then I plus 1. All right, cool. And then really it's the same for I could probably make this a little bit neater, but so this just becomes sorry. I think it's probably yeah. It was in here. Okay, let's try that. Above is 2. Length of mirror minus below is 3. There we go. Okay. I think the same thing down here. As we've got a count versus an index. All right, so I think our row 1 is working. Our column 1 does not seem to be working. So let's dive in to that. Okay, which mirror are we looking at here? We want to look at, in this case, we're saying for a given row line, we're looking at, yeah, because we're looking at everything in J, which are these, did I luck out and 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, we're looking at the above line and the below line, and for each character in it. I'm having such a hard time thinking about it this way. So if we wanted to go back to our draw here for a second, and right now we have this one working. And so if we think about it in this context instead, and we're starting here and here, we want to start with 0, 1, 2, 3, 4, 5, 6. Okay. So we want J to cycle through all the rows, which is what we're doing here. And then we want to check as we're cycling through all the rows. Where did this index out of bounds come from? So we want J to change because we're going to be cycling through here. 0, 1, 2, 3, 4, 5, 6. And the above should be on the left. No, that should be on the right. So what am I doing wrong? Do I have this context wrong? So this is the row, or this is the width of it, and we want -1 and above. So let me see here. Let's debug real quick. Valid call reflection checks are 3. So our mirror here is 7. Okay. So we know we want 7 is valid. And we're going to range through J. So we're going to go from top to bottom. And our above is 4. And our below is 5. So that means we should be going 2 out. Why do I have 3? 5. Okay, that's good. So we should be at 1, 4, 0. Okay. Is it returning false? That's my question. Yes. So, y, j of 0 above 4 plus 1 is 5. Ah. That's what I messed up. Okay. Let's try that again. Nice. All right. Let's take a look at our test input, or our actual input rather. Let's bring that over here. Plug it here. And let's run day 13. Index out of range, 7 with length 7. Okay. I think there's a problem with, so we get a length of mirror minus 1 minus whatever the below value is, whichever one is min. Index out of range 7 with length 7. If above minus I is less than 1 or below plus I is greater than length of mirror minus 1. I mean, that should prevent it. I don't understand why it would not. We're not manipulating above or below here. I do suppose that this should be sub-0, perhaps, because it may not be the above and below. Can we get rid of this? I'm also going to get rid of this. Yeah, that was the issue because, okay. So 3356. Awesome. Great stuff. All right, moving on to part 2. Part 2, you resume walking through the value mirrors and smack, run directly into one. Hopefully nobody was watching because they must have been pretty embarrassing. Upon close inspection, you discover that every mirror has exactly one smudge. Exactly one. Should be the opposite side. In each pattern, you'll need to locate and fix the smudge that caused a different reflection value line to be valid. The old reflection line won't necessarily continue being valid after the smudge is fixed. Here's the above example again. The first pattern smudge is in the top left corner. It would have a different horizontal line of reflection, yada yada yada, with the smudge in the top left corner. Paired, a new horizontal line of reflection between rows 3 and 4 now exists. Row 7 has no corresponding reflection row and can be ignored, but every other row match exactly one row will match the second pattern. The smudge can be fixed by changing the fifth symbol. All right, so given the same set of input, let's look at our test, and then let's talk about how we're going to implement. So 400, and there's this idea that you can somehow, there's only one imperfection in the entire thing, and so we can do something like this where we have imperfections 0, and we can do imperfections ++. So each time we find something that is not that, and we'll say if imperfections greater than 0, return false. We'll do that instead. Yeah, greater than allowed imperfections. Then we return false, otherwise we return true, so that when we're validating. And this is going to be for the entire thing of matching, so that if at any point we'll allow an imperfection and we'll keep going, but if there's more than one, and then we're going to do the same thing up here. Allowed imperfections, and we'll change this to be this, and we will have this as this. Okay, so that's kind of part of the story, but there's one like last kind of piece here. So we're going to pass this down to the underlying bits because I want to make sure that if we find a reflection point that's perfect, say the center point is perfect, we need to make sure we reflection, because it doesn't matter if it's all spelled the same, right? Reflection. But I want to make sure that we validate the whole thing. But then we'll take one last step here, and that is we need to do the same for this. So zero, and then for the center point, the same thing. If imperfections greater than allowed imperfections matches false, and we will imperfections ++. So that will be on that line. The one difference here is for the matching. Since we're indexing forward, we want to, for each row that we're looking at, we need to recalculate this because this is just for the center point. And then the same thing down here. So that is true. And then imperfections. Oh, I suppose I could break here too. That would be fine. And then as far as the allowed imperfections go, we're just going to pass this through. Maybe we should be fine. I think this is the probably the better way to do it. And then we'll just add it as a variable to our test. 0 imperfections are allowed in the first one. And then on the next one, we allow 1 imperfection, and the pattern of this function changes. And that way we can also go test dot allowed imperfections, and we run it, and we actually ran it. We want that. So hopefully. Okay, so that passes. And then for our second bit, part 2, we run it with 1 imperfection allowed. And we get 37,523. 37,523. All right, my video crashed again. I don't know why, but that's okay. What did I do wrong? So formula reflection, imperfections are reset on each row that we're looking at. And we increment our imperfections every time we find something that doesn't match. If our imperfections are above our allowed imperfections, our match is false. Only then do we want to break out. Okay, that's fair. I think it still lets my test pass. Okay. 37,523. It's still the same value. That is what I put in, right? Okay. Hold on. Let me just see here. Now the pattern has a different horizontal line of reflection between rows 1 and 2. Okay. Well, here we are. So my guess is that we're dealing with something where the vertical changes because the only 2 examples they have in the test are of horizontal. So if we go to our input, let's just look at our code for a second and see if we can see something with that. So imperfections gets reset here. And then for each one, we're going to loop through and we're going to increment the imperfections where they don't match. And only if the imperfections grow above the allowed imperfection mark will the match become false. And just to make sure there's exactly which is true, we pass in the allowed imperfections and we look again. We would start with the first line, which would be the alleged imperfection. So we're going through each record row. We're comparing row by row, each value. And if there's an imperfection, we increment it. If the imperfection is greater than our allowed imperfections, this is 1 and this is 1, that's fine. This is 1, this is 0, that's fine. This is 1 and this is 2, that's not fine. We set match equal false and we break. We break this loop. If match is still true, we seek a valid row reflection. And if that's true, we return the row and the value. So valid row reflection, we pass in our allowed imperfections. And in totality, we are checking the imperfections. And if they grow above our allowed imperfections, we return false. Otherwise, we return true. The same is true here for the columns. So why? Say my number was too high. Yeah. Well, here we are again with some set of inputs, and one change can alter the course of the input. So, what's the best way to do this? Let's do this. Let's grab this, and I'm going to create just a debug function real quick, and then what I'm going to do is I'm assuming that everything is going to have a new reflection line. And then I'm going to call I pass 0 in. Okay, let's see here. Okay, I think I figured out the magic sauce. So the instructions said that there has to be at least one imperfection. So we can't return true here unless we have at least one imperfection. And so I think that is our missing link here. It's not that they're allowed to have at least one imperfection. It's that we're looking for the one that, if changed, will give us a new line. And so I think that is what's going on here. And then we should also see that here. So we can change this as such. And if we test, okay. Let's look at our result here. Okay. Smudge top corner paired new horizontal line of the reflection between rows 3 and 4 now exists. Row 7 has no corresponding reflection. Row 1 matches. Horizontal line reflection. Okay, so we're forcing the imperfections. Imperfections should equal our allowed imperfections. me just make sure on our test input. Instead of using the new different reflection lines, example, the first pattern's new horizontal line row has 3 rows above it, and second pattern has 1 row above it. It's possible that I'm actually getting 0 and 4. Got it. So we're not finding, okay, so my test is misleading because we're actually not finding an imperfection. We should be finding this. Okay, wait a second. Is that the answer? The smudge in the top left. Okay, so we actually don't care about the imperfection at the reflection line per se. We care about we do kind of care about it because they're only allowed 1, but we don't expect there could be 0 at the reflection line. So if I rerun this now, I don't care about debug. That's much less than before. Okay, boom, got it. All right, so the hang up there was that if we go back to our diagram, I was requiring that the reflection line, which is the center point, have the imperfection. But that's not actually what the requirement was. The requirement was that one of the things in the reflection were messed up. So I kind of got lucky with this first example because the imperfection, or you saw the test failed once I added the requirement to the code. But if we come to this example here, what was going on is we got to this reflection line here and here, and my requirement in code that I put in was that there had to have been an imperfection here. But the imperfection wasn't here. The imperfection was up here. And so if you look at the whole reflection holistically, there's only one correction, which is this top right corner. Right here. So the issue, and we can highlight it down here as well. So the issue came into play that I was requiring only one in the reflection line. So let's clean things up real quick and let's go with a quick review. We're going to get rid of debug. All right. So part 1, pretty straightforward. We are looking for any mirror that has a reflection, and so what we're doing is I created this method called find reflection. Depending on what kind of reflection it is, if it's column based, it's just adding. If it's row based, we times it by 100, and that's it. If we don't have a reflection, that's kind of bad news. So let's look at find reflection. I think relatively straightforward. We're looping through all of the rows, and we went ahead and just added to this to allowed perfections, but we're looping through all the rows. And if we find if we're over our number of reflections, our allowed imperfections, we exit, but we count our number of imperfections and we pass in how many are allowed. So in part 1 case, then that's 0. Part 2, that's 1. So it's the same functions. If we get a match, meaning everything is matched at the center point, that still doesn't prove that it's an actual reflection. So in order to do that, we have to go through and validate, like what we see here, that we have a mirrored reflection. The difference between part 1 and part 2 is just the fact that we're allowing one smudge on the mirror. And then finally, that gets validated. And if we're valid, then we return that row. If we don't find a match on the row, we repeat the same for the column. I think really I could just rotate the grid. That's easier in some languages like Python with some built-in. You could do it in Go. I just didn't really want to do it. So let's talk about our validate row reflection. All this does is figure out how many integers we have to move outward from the center point. And then I went ahead and just included the center point in that. We're checking it a second time, but that's okay. That was actually was unintended, but really it's intended because the mirror line itself could have the imperfection. And the rule is that if you have a mirror, they have to be even number of rows or columns, but it doesn't have to go to the very edge. So like in this example, we don't include this last row because we're at the edge in the top portion of the mirror. So we only have to validate those two sections. So we crawl outwardly from the inside, checking to make sure that they're all added up. And then we do the same thing for columns, just, columns instead of rows. And then based on the score, based on what is returned, we score it appropriately. And that's pretty much it. So hope you got something from this video. If you like the content here, please like and subscribe. My goal of these videos is not just to complete the puzzle, but to walk you through my thought process and walk you through my decision making. While it may be imperfect, it kind of helps to understand where I've made mistakes, but frankly, just understand how we think through these different problems and challenges and kind of can come to an answer. So if you hit that like and subscribe button, we'll be happy to put out more content. But as always, over and out.